Alright, welcome to your first video lecture. This is going to just be a brief intro to the mathematics of AP Chemistry and just a reminder of some of the key things like some of your formulas and definitely about significant figures. We'll be using those all year. So the reason that we use sig figs or significant figures is because not all of our measurements are going to have the same number of graduations or have the same amount of accuracy. So you really want to tell the truth when you're talking numbers in chemistry, because if you report a number, we expect that it's to everything is precise to one estimated digit. So inherently there's always a little bit of uncertainty in reported measurements, but it's a standardized uncertainty to one estimated digit. And then also we're going to talk about rounding a little bit, rounding in the fact that we're going to use mainly the same rounding system that you normally would, where you have, if it's above 5, you round up. If it's below 5, you round down. But rounding is really going to be the thing we're going to use in calculations. I apologize for my penmanship. I have a new device that I'm working on, so forgive me. Alright, so when we talk about measurements, you'll see that we have this kind of metal piece right here. Maybe it's aluminum, magnesium, something like that. And this is being measured with a ruler that has no graduations. You can see there's no little dashed lines all the way around here. So if we do know that you start off at 0 centimeters and the end over here is 1 centimeter, well, we have to kind of guesstimate what this length is. So I'm going to say it's about 1/5 of the way down. You might say it's 1/4 of the way down. But because there's no graduations, we're only allowed to use one digit here, one significant figure. So I'm going to say it's 0.2 centimeters, whereas you might say it's 0.3 centimeters. So the real reason that we're talking in kind of in this way here is the fact that you see there's one sig fig here and there's one sig fig here, and that's because there are no graduations at all. That one sig fig that we've noted here is the estimated digit. Okay, so it's one estimated digit greater than the measuring device graduations. The second ruler we have here, you see it's got graduations all the way from 0 to 1 centimeter. There are 10 graduations there, meaning that every one of these is 0.1, 0.2, 0.3, blah, blah, blah. But as you know, we know for sure that this piece of metal is definitely up to 0.2. We're allowed one estimated digit after that. So I'm going to call it, let's say, 0.27. You might say 0.28, someone else might say 0.26, but that estimated digit, that's our flexibility, that's our inherent uncertainty. This last one down here has many, many, many graduations. That's a lot smaller scale. So we know for sure that it is 0.2, 1, 2, 3, 4, 5, 6, 7. But we need to specify one estimated digit. I might call it 2.70 to indicate my estimated digit. Someone else might call it 71 centimeters. And you notice that I'm putting units on all of the measurements that I'm making because it's not a measurement unless it has a unit with it. And all of your instruments and equipment will have the unit indicated. So the information down here talks about the device's measurements. Alright, so we also have thermometers. We'll be using thermometers like this. We'll also be using probes that have a digital readout, which will have their own significant figures already indicated. But if we just look at these 3 examples here, we see that this is measured at 4 degrees Celsius, and that's because we have given to us measurements of 1 through 5 right here. So we know for sure that it's at a 4, and the person whoever measured this indicated that their estimated digit was 0.0. So all of these are to 1 sig fig, but we're going to indicate our measurement to 2 sig figs where 1 is an estimated digit. Same thing here. Actually, this is somehow not to the correct value here. We've got 8.3 about here. So apparently this was squiggled in here. It's filled up to that, where we know for sure it's at the 8, but then we have to estimate our last digit, which is the 3 here. So here's our estimated digit, and lastly, we've got 64, call that right there, and the information on the graduations here, and here. all show us 1 sig fig, so we are allowed to report to 2 sig figs, which is why we have 64, or our estimated digit is the 4. All right, so a lot of instruments and equipment that we'll use will have a plus or minus maybe listed on it, where it's maybe plus or minus 1 degree or plus or minus 0.1 degrees Celsius. So the instrument can be more precise or less precise, so be on the lookout for those errors of the plus or minus in the measurement. All right, so I've been talking about sig figs, and I actually taught some of you guys, so I've talked about the Pacific and Atlantic method, where this is a really easy way to remember how to count significant figures in measurement. So in this method, if you have a decimal present in the number or the measurement, then you're going to approach when you're counting out your sig figs, you're going to approach from the Pacific. So if we have the United States, we know that we have the Pacific over here and the Atlantic over here in terms of the oceans. So if you have something like 5,001.2, you're going to see that you're going to start from the Pacific side and count all of your digits, because the first number that we have is a 5, and it is a non-zero number. So we would have 5 sig figs here, 5 sig figs. But for example, if you have maybe 0.00123, the decimal is present, you're also going to start from the Pacific. You're going to start over here, but the first non-zero digit is actually the 1 here, so you're only going to have 1, 2, 3 sig figs in this number. All right, so we also have another approach where we have it if the decimal is absent. So maybe I'm just going to give you 5,000. 5,000, there's no decimal present, therefore we're going to start from the Atlantic. We start from the Atlantic, we start counting the first non-zero digit, which is that 5. That 5 is the only sig fig, so there's 1 sig fig, significant figure in that number. Let's do some practice problems. All right, so here we have the decimals present. When you start counting from the Pacific, you see that you have 2 zeros. They do not count. The only 2 sig figs here are the 6 and the 7. Same deal here. You start from the Pacific. When you see these 2 zeros, they are not significant figures. You start counting when you hit the first non-zero digit. That is the 6, 7, and the 0. This time the 0 is significant because it comes after some significant digits, meaning that it's telling you it's precisely 0.00670. It's not only to 2 sig figs, which would be less accurate. Down here we see the decimals absent. You start from the Atlantic. You skip over the 2 zeros because you do not start counting until you hit the first non-zero digit. Going this way, you see you have 1, 2, 3 digits. We have 3 sig figs here as well. All right, also present, start from Pacific, 3 non-zero digits here. Starting from the first non-zero digit, that is also 3 sig figs. Continuing, it's present. We actually get to start counting at the 1. We go all the way. There are 3 sig figs. Starting here, the decimal is present. Once we start from the Pacific over here, you start counting at the first non-zero digit, which is the 8. 800. Those are the 3 sig figs here. This one is absent since there's no decimal here at the end, indicating that it's exactly 430. So this is our estimated digit. Therefore, we're going to only count the two digits here, so there's only 2 significant figures. This decimal here tells you it is exactly 430 to the knowledge of whatever we're using to measure. So that decimal is present. We start from the Pacific, we go to the right, and we're going to see 3 sig figs here. If you need some help with that, there's a lot of good information in your textbook. All right, so that's just counting sig figs. If we want to actually use it in terms of calculations, it's used in 2 different ways. When you're multiplying and dividing, you actually have to count your sig figs in all of the measurements that you have. I don't have measurements indicated here because there are no units. We're going to talk about units here in just a minute. In this case, we have 3.887, which has 4 sig figs in it. I counted it really quickly. You start from the Pacific. I start with the first non-zero digit. All 4 of those are significant. This number here, I see there's a decimal present. I start from the Pacific, and there's 3 significant figures. When I multiply these two, the one that is my weakest link, it's kind of the way I refer to it, the weakest link is going to be the 3 sig figs, meaning my final answer must be in 3 sig figs. And that's to eliminate some of the lies we tell with our numbers. We don't want to indicate to someone that we know for sure that a digit is precise when actually it's an estimated digit due to some calculations. So when we get here, we see 60.2485 is, when you're calculating, you extend your decimals a bit. But we only can count 3 sig figs. So we're only going to record to 60.2. Now, if this 4 had been a 5, it would have rounded that up to a 3, but it's not in this case. So I just used a rounding in this case here, so just to be aware of that. When you only can record 3 sig figs, you do have to look at the 4th digit present to see if it rounds up or if it stays as is. This is different when you're using addition and subtraction. You actually don't count significant figures at all. You're going to be using decimals. Okay, so that's a little bit different here. So in this case, your weakest link is going to be the one with the lowest number of decimals. Here I only see 2 decimals. Here I see 1 decimal. So this one's going to be my weakest link, meaning that my final answer after I've added or subtracted, I need to only have 1 decimal here. That's pretty easy. I see 12.7, and that's it. If this number, instead of being 12.71, it had been 12.77, when I created the correct number of digits here, I would have actually seen that this last digit would have caused the previous digit to round up, and it would have been 12.8. There's still only 1 decimal here and 1 decimal here. It's just the matter of making sure you look at the next digit if it rounds or not. Alright, so we're going to be doing things and calculations that are a lot harder than those that I just indicated to you, and I just want to make sure that you carry out your significant figures all the way correctly. So what I do is I actually keep it in my calculator. I keep the number and I go back and I highlight that number, and it's probably a number I usually have 4 or 5, maybe 10 decimals depending on how I've got the settings set up in my calculator. I'm going to keep all those decimals all the time because I can do something early on. I can round too early and I'll get something called rounding error. Okay, and that's going to make your number different than mine or different than your neighbor. So you definitely want to keep all your decimals and all your numbers long until the very, very end. At the end, when you want to create the appropriate number of sig figs in your final answer, you go back, you look and see, oh, you had 2 sig figs in this number, 5 in this one, 6 in this one, and 4 in another one. So if you're doing multiplication and division the whole time, the weakest link would be your 2 sig fig number, meaning your final answer will have to be to 2 significant figures. If you've got some addition and subtraction and some multiplication or division, you're going to have to kind of just be careful and looking to see after you subtracted something, it maybe should have only had 2 decimals, and how that will affect your final answer. Okay. Now, significant figures are only significant in measurements. That means something with a unit and something that we have determined through experimentation or through some instrument. Okay. Mole ratios, they're not significant figures. In our metric conversions, yes, they are. They do have units, but they're not a measurement. They're simply a unit conversion. Okay, ignore those for your sig figs because you're gonna get too many significant figures or too little. So you don't want those to be implicated in your final answer. They're just used for conversions only. All right. So speaking of units, we've got our international system of units called the SI system. We've got units of measurement and we are going to use certain bases. So for length, we're going to use meters. It's labeled M. If you've got mass, you actually use kilograms, not grams. A lot of people think it's just grams, but we're going to use kilograms. Time, we have seconds. That's just an S. Kelvin, we all should know Kelvin is a capital K. That's our temperature unit. And we'll probably use degrees Celsius quite a bit as well, but we don't actually call that our SI unit. We do use it because we have thermometers that measure in it. And then volume, we have liters and meters cubed. So we have liters and meters cubed. And sometimes we'll have something called a derived unit. And a derived unit is one that's actually derived from these bases or units here, but maybe something like grams per milliliter, and that's going to be density. So grams per milliliter is a derived unit because calculations are involved to attain it. All right, so if you want to talk about the metric system, which is what we'll use all the time in chemistry, you already know your basic set of prefixes. Prefixes, you know, are going to be used in front of some base, in front of meter or gram or liter. So this is kilo, hecto, deca, base, and the base unit are those ones that was on the previous slide. Deci, centi, milli. That's the easy peasy version. These are all based off of power of 10, so as you move down the number line, you're moving the decimal. The cheesy way to remember it is King Henry died by, so you see we're getting in lowercase now, drinking chocolate milk. We're going to use a bigger, badder version of this in AP. And here we go. So here's our more advanced version. I've got spaces here to indicate to you that there are different prefixes here, but we don't use them that commonly. They're in your textbook, but we just don't use them. So all these spaces are prefixes. I just skip them so you don't have to memorize them. So here's our more advanced one. We've got King Henry died by drinking chocolate milk, ... micro. Micro is 10 to the negative 6, ... nano, and that's, sorry, you can't see the 6. That's 10 to the negative 9, so you should be remembering nano 9. That's pretty easy. And then ... pico. Okay, that's 10 to the negative 12. So these are really tiny measurements on this side. If you go 3 decimals in front of the kilo, kilo is 1,000, which is 10 to the 3rd. This is mega. Mega is a capital M, it's 10 to the 6th. Okay, so these are going to be ones that we will commonly use. You'll see micro a lot, and you'll actually see mega a bit, especially in some of the introductory questions, math questions you'll be using. So this is the bigger, badder version of the metric system. Make sure you know it. Temperature is interesting because a lot of people think it's heat. It's not. It's actually energy called kinetic energy, which is energy of movement or motion. Okay, so when particles are moving around, they have a specific amount of kinetic energy, and when we measure that, we're actually measuring the amount of kinetic energy, which we report as temperature. In the SI system, we have the Kelvin scale, and that's going to be using our K again. And don't forget, whenever you're converting from degrees Celsius, you just add 273 to a number, and you're going to get the Kelvin temperature. We don't use a little degree mark when we talk about Kelvin. And the reason that we use Kelvin, the Kelvin scale, is because that we sometimes will refer to absolute zero. And absolute zero is 0 Kelvin, and that's the lowest value of temperature that was thought to possibly exist. That's where all movement stops. That's where the entropy, I don't know if you remember that from Chem 1, is the amount of disorder of a system. This is the minimum energy, entropy possible. So the minimum, the absolute, there's no motion at all, there's no kinetic energy involved. So that's pretty neat. That's the reason we use the Kelvin system. Okay, and then we talk about Fahrenheit very, very, very rarely. We don't say the F word in AP Chem that much, but we do use Celsius, especially when we get to thermochemistry. I told you earlier, no degree symbol on Kelvin, only on Celsius. And the conversions for that are here. We've got from Fahrenheit to Celsius. Fahrenheit is equal to 9/5 times the sum of degree C plus 32. So if you're converting from Celsius to Fahrenheit, that's how you do that. Kind of the inverse of that, you have if you have Fahrenheit and you want to get to Celsius, that's this. These we don't use as much, but we do definitely use this from converting from degrees Celsius to Kelvin. So you add your 273 there. This is all should be review. Density, this is just a common derived unit that we will use quite a bit, especially in our first lab. Density is mass divided by volume. So that might be grams divided by milliliters. That might be kilograms divided by liters. That might be grams divided by centimeters cubed. Where centimeters cubed is, you know, you have a box, you have maybe a cube here, you've got length times width times height, where the height is there. So you've got all your measurements, and it's the volumetric volume of it. All right, so that's listed all here. Check, we've got that. It's the ratio of the mass to the volume. All right, so practice question real quickly, just so you remember, how do you calculate the density of a regular? So this is where we know how to calculate the volume of an object. So we've got a rectangular prism here. We know that density is mass over volume. We have the mass given to us here, which is 827 grams. The volume, on the other hand, we have to calculate. So we know that volume of a rectangular prism is length times width times height. So I'm just going to use the numbers here, 5.0 centimeters times 4.0 centimeters times 10.0 centimeters. And I've got the units here all the way, because we know that the volume here needs to be in centimeters cubed. So when you calculate that, you actually get 200 centimeters cubed. And you'll see that we only have 2 sig figs, 2 sig figs, and 3 sig figs here, where the weakest link for us is going to be 2 sig figs, because this is a multiplication problem. So I'm going to rewrite this as 827 grams over 2.0, 2 sig figs here, times 10 to the second centimeters cubed. All right, so once we do our division here, you'll see that we now have density is equal to 4.1 grams per centimeter cubed. And the final answer is in how many sig figs? It's in 2 sig figs, and that is good because our weakest link would have been the volume here, being the 2.0. This up here has 3 sig figs, so the weakest link was the 2 sig figs, and that is going to indicate our final answer, sig figs. All right, so what if we have an irregular shaped object, something that's not just a standard volume calculation? We would use volume displacement or water displacement method. That's going to be like, for example, if you have a cylinder, a graduated cylinder. It's my nice, beautiful graduated cylinder here. I got my graduations on it. Okay, and I drop a rock in it. So I'm going to label this. I'm going to drop a rock down in here. It's kind of got crazy shapes and stuff on it. It looks lovely. Okay, so once I drop my rock in there, say before I had 20 milliliters of water. When I drop my rock, it now gets up to 35 milliliters of water. That's going to be the volume of 15 milliliters of water that was displaced. That's how you measure your volume displacement, which would then just give you the volume of the object, the irregular shaped object. So in this case, we have an example of 20 grams mass over volume, 20 grams. How many sig figs here? 1 sig fig, because that 0 is starting from the Atlantic side because your decimal is absent. Only the 2 is significant. Over displacement of 40 mils of water, 40 milliliters of water, also 1 sig fig. That's going to give us just 0.5 grams per milliliter. Making sure that you're showing me somehow that this is the final answer, and noting that I only have 1 sig fig here as well because of the fact that I had 1 sig fig in both of my previous measurements. 1 sig fig in the end. All right, so error analysis. We usually talk about 2 words a lot in AP Chemistry. We talk about accuracy and precision. I really hope that you guys have precise measurements and they are also accurate, but you can also have really precise measurements, but they're not accurate whatsoever. So, for example, you're Michael Jordan and you want to be accurate in your shot, you're going to hit the basket. The basket is the true value, and it's the true value that you desire. It's going to be maybe published in a book or just known to the games of basketball. If you want to be accurate, you got to hit the basket. But precision is also a really good thing. So you want your values of measurement to be precise because that means you're doing the procedure correctly. That means your balance is calibrated. That means that there's no goofy errors that are occurring. So precision is also very good. And that is just a way to say that all your measurements are in the same range. So maybe you measured 100 measurements and they're all between 2 centimeters and 3 centimeters. Okay, maybe the accurate value is over here at 5 centimeters, Okay, so you're not accurate, but all your measurements are falling in between here. That means you're doing the right thing, just maybe something's off in the instrumentation you're using. In basketball, to be really precise, maybe you hit the upper right-hand quadrant of the backboard 100 times. You're super precise, but you just never actually make the basket, so you're not accurate. So that should be fairly easy, just some vocab terms to know. All right, so looking at this example here, student collects the following measurements of copper wire. You can see that the student has 3 sig figs in all of his measurements, his or her measurements. But the actual measurement, the actual true value, that says true, value is 25.5. All of his measurements were really close together. Okay, so they're really precise. They're just not accurate. So were the student's measurements accurate, precise, or both or neither? Just precise, not accurate. All right, so we're getting towards the end here. We have error and analysis. We are going to use percent error all the time. In all of our labs, we will. Anytime that I give you an actual value, this is something published in a book usually, this is going to be the value that I really want you to get. This is what you did. Okay, what you got in the lab, you're going to figure out your percent error. So this is true. Minus the experimental value, which you've gotten. The absolute value of that, you don't want a negative percent. You just want to tell me the percent error. It doesn't matter if it's up or down from that usually. Divided by the actual or true value again, times 100. That's going to give you a percent error. Occasionally, you'll see something like this published, where you have a value that you achieved, and then plus or minus some error. This is a small amount of error. This is great if you know how precise all of your instruments were, your pieces of equipment. If you have maybe like an Erlenmeyer flask, a beaker, or a graduated cylinder, of these three, the graduated cylinder is the best. If you're trying to measure volume with a 250 milliliter Erlenmeyer flask, you're doing it wrong, because the actual precision of that, it's very low. You know, you could be off up to 25 milliliters. That's horrible, okay? If you want a really accurate volume, then you're going to use a burette. Burettes have something like 0.01 milliliters error, plus or minus. So those are super great, and that's what we'll use in titrations. So this just indicates really to you how precise your instrument is that you're measuring with. All right, so last question on error analysis. For our students measuring the 25.5 centimeters length of wire, what's the percent error? What are you going to do? You're going to do actual minus experimental over actual times 100 to get percent error. So actual would be the 25.5, experimental would be the 19.8, and you want to know the percent error. So here we go. Actual minus experimental over actual times 100, that's 22%. And just making sure we're sticking with our sig figs, you can see that 25.5 minus 19.8 is going to give us this is an addition and subtraction, and then we've got division here. So if you're looking here, you can see that we have 5, let me find some ways to write this. Top number is 5.7. And you have 1 decimal here, 1 decimal here. Both of them are equally weak, meaning you have 1 decimal in your final answer, divided by 25.5 times 100. So we've got a new scenario here. This one has 2 sig figs. This one has 3 sig figs. The weakest of them both is the 2 sig figs, meaning you should have 22, 1, 2, 2 sig figs in your final answer. And I usually don't care too much if you put units or not, okay, because this is a percent, and most of the time we do not use units in percents. Scientific notation. This is one thing that you should be very familiar with. You've used it probably since middle school. You always have a front integer between 1 and 10. You always have to make sure you conserve your sig figs. This is something probably new for some of you guys. In your scientific notation, and you want to make sure that you've used the appropriate exponent. Okay, so scientific notation is different than exponential notation, which we usually will not use. So looking at our first number, we see our 3 sig figs. 3 sig figs are 4, 5, and 0. What I did was I counted from the Pacific. I looked until I saw a non-zero digit. That was a 4, 5, and 0. So when I write this out in scientific notation, I'm going to have to note a number between 1 and 10. That's going to be 4.50. But I also need to notate the scale of this. So this is an itty-bitty number. So to count backwards, we see that we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 decimals in front of that, meaning this is how we need to write this. Oh, 1, 2, 3, 4, 5, 6, 7. Oops, sorry, I counted that wrong. Here it is. All right, and then notice this. We've got just our sig figs notated here as 3 significant figures. All right, looking here, this is nice and concise. This is how we will normally write numbers. We don't want really long numbers because it gets pretty tedious to write out all those zeros. That means we need, this needs to be 6 decimals to the right because it's a positive 6. So when you write this, you're going to have 1 decimal swoop here, 1, 2, and then we need 4 more. So your new number should look like this, 3,810,000, done, okay? We see our 3 sig figs still conserved here. 3 sig figs, 3 sig figs. 3 sig figs again, but we're going in the negative direction to the left, so we should be moving our decimal point 4 places to the left. When you look at your final answer, you've got 0.000966. 3 sig figs are notated here as well. All right, and then this one, I want you to record this to 3 sig figs. Knowing that you need to write in scientific notation, you should be seeing that you want to have the 7.5 notated, but we need 3 sig figs, so that means I'm going to keep that extra 0 there, and so when I write it, I'm going to write 7.5 times 10 to the 7th. That's an exponent there. All right, so scientific notation just makes your life easier. You don't have to write so much out. Data types, this is pretty easy. Quantitative, quant, you've got it in there. You're going to be using numbers and quantities. This is always going to be, your measurements are quantitative data. If I want qualitative data, I want qualities. That's something like something was this, was tall versus short, or something was explosive versus non-reactive, something was blue versus black. Usually colors and sizes are going to be the descriptions that you use. All right, we're getting to the grand finale here, the mole. I'm just going to give you a brief intro to the mole, Avogadro's number, and a couple of conversions. So Avogadro actually didn't discover the 6.022 times 10 to the 23 particles per mole, but he is given credit for it in the fact that we name it after him. So when we talk about these, we're talking about units and how we're going to be converting. So the mole is the standard unit of measurement in chemistry because it's going to be describing a humongous number of particles. But when I say particle, you're thinking, what in the heck is she talking about? So particles are going to be things like atoms, molecules, and I abbreviate molecules, MOLE', and formula units. Formula units are going to only be used for ionic things. Molecules are going to be only the term we'll use for covalent things, and atoms are going to be used for elements. So these are particles. So per mole, you're going to have Avogadro's number of atoms per mole of an element such as copper. You're going to have Avogadro's number of molecules per mole of carbon tetrachloride. You're going to have Avogadro's number 6.022 times 10 to the 23 formula units of sodium chloride. So these terms are very specific to the type of bond or compound they are, and if it's an element or not. All right, so this bit here is talking about conversion. So if we have molar mass, and I want you to take it to something else, take it to the number of moles that represents the number of atoms that represents. It's a very standard way of doing it. We call it dimensional analysis. I'm sure you all loved it when you're in Chem 1. So say we have carbon dioxide, and I give you 44 grams of carbon dioxide. See how I know the number, the unit, and the identity of the thing that we're talking about? If I have 44 grams of carbon dioxide and I want you to convert it to moles, I do it like this. 1 mole of carbon dioxide is equal to 44 grams of carbon dioxide. And I chose this number because I knew that was the molar mass of carbon dioxide. Carbon, which weighs 12, oxygen, which weighs 16, add it together, 2 oxygens at that, and that's going to give you 44. Okay, the reason I do it this way is because I can show my cancellation of units, and I've officially just converted that to 1 mole of CO2, carbon dioxide. Okay, this is dimensional analysis. You may use the fence post method. I do not care. It works for me. All right, so now I want you to convert to atoms. And I don't like this because I chose an example that used not atoms but molecules. So let's change this and do molecules. Okay, here we go. So I have, if I want to go to molecules, that means particles. So that means I'm going to use Avogadro's number, 6.022 times 10 to the 23rd molecules of CO2 per 1 mole. This is where my handwriting is getting lovely, so forgive me here. 1 mole of CO2. Alright, and the reason I do this is because I want to be able to cancel out units, so I have some mole of CO2 on top, mole of CO2 on bottom. That's going to leave me with Avogadro's number, which is 6.022 times 10 to the 23rd molecules of CO2. Okay, so you have to show your work for me. You have to show your units for me. The identity matters sometimes, not all the time, so just use your best judgment for that. And I'll usually will help you and tell you what I need you to do on that as well. Okay, last thing, so our example problem on how you do conversions between moles, moles of a compound, moles of an element, formula units, etc. So let's do this last bit here. So I give you an amount. I have 4 sig figs here, so that's good to know, of ammonium sulfate. Ammonium is NH4 plus. Sulfate is SO4 2 minus. But when I crisscross, because it's an ionic compound, I get NH4 2, so here I put parentheses around my polyatomic ion, sulfate. So this is the compound that I'm talking about. It's an ionic compound. If I give you 0.6331 grams of ammonium sulfate, and I'm actually going to write it out here, and you need to convert that to moles because that's the unknown. I'm going to put moles on top, so I know that 1 mole of ammonium sulfate contains a specific number of grams. All I have to do is add that up. Nitrogen weighs 14, 0.01 or something like that. Hydrogen weighs 1.008, and sulfur weighs 32.06. Oxygen weighs 16.0. Make sure you multiply by the indicated subscripts here, and you're going to get a molar mass of 132.08 grams of ammonium sulfate. I've officially canceled out grams of ammonium sulfate. When I do the math in my calculator, I get 0.004793 moles of ammonium sulfate. And I'm a scientific notation person, so I like to write it as 4.793 times 10 to the negative 3 moles, okay? And that's how I have my calculator set up, so whichever way you like to do it, I prefer scientific notation, that's fine with me. You'll see that I had 4 sig figs to begin with, and I have 4 sig figs in the end. I also had 5 sig figs in my molar mass, but that's not important. It's not needed because that's not going to be our weakest link. Alright, so now I want to go to moles of hydrogen atoms. That means I'm going to dig into an individual ammonium sulfate formula unit. Okay, I already have my moles here, so I'm going to start with this number. I'm going to write 4.793 times 10 to the negative 3 moles of ammonium sulfate. I'm glad you can read my chicken scratch here. And I know that it's only asking me for hydrogen atoms, meaning I have right here, I have 8 atoms of hydrogen in an ammonium sulfate formula unit. Okay, so this is how our moles is what I'm looking for. So how I'm going to do it is I'm going to use 1 mole of ammonium sulfate, and in 1 mole of that I should also have 8 moles of hydrogen. Okay, if I had 1 formula unit of that, I would call that 8 atoms of hydrogen. Because I have moles here, I wanted to cancel that out and put moles there, and I have moles of H on top, which is the desired unit. That's 3.8 0.35 times 10 to the negative 2 moles of H. Okay, that's moles of H. That's hydrogen atom. Okay, that's our final answer. You'll see again we have 4 sig figs. That's because we had 4 sig figs here. These were just mole ratios, so they're not measurements. All right, let's get down to formula units. And formula units is just a term used to describe an ionic compound, which is ammonium sulfate. So here we go. We're going to start with our our moles, 4.793 times 10 to the negative 3 moles of ammonium sulfate. And when I say formula units, you should be thinking particles. Okay, particles is going to be related to Avogadro's number, meaning 1 mole of any substance is going to be containing 6.022 times 10 to the 23 formula units of NH4 to SO4. Okay, this is looking great right now. Okay, so all you're going to do is multiply across. Make sure you put in your calculator 4.0793 times 10 to the negative 3 in parentheses times Avogadro's number in parentheses. It doesn't matter during multiplication, but get in the habit of it, because when you get to division and you don't put your parentheses in the correct spot in your calculator, you're going to get a funky number, and you don't want that. All right, so the final answer for this one is 2.886 times 10 to the negative 2. Oh, I just lied to you. Times 10 to the 21st formula units of NH4 to SO4. All right, we're getting down to the end here. Nitrogen atoms. Now this is where I actually want to know the number of atoms, which means to me a particle, which should be ringing the bell of Avogadro's number again. In this case, I'm going to start again with my 4.793 times 10 to the negative 3 moles of ammonium sulfate. And I need to go ahead and get to something smaller. So a smaller kind of component of the ammonium sulfate would be moles of nitrogen. So let's do like we did above with the hydrogen. 1 mole of ammonium sulfate, 4,2SO4, has how many moles of nitrogen? I see this 2 here, subscript, is referring to 2 nitrogen moles. So 2 moles of N. All right, that's great, because now I can go straight to atoms of N, of nitrogen, because I know that 1 mole of nitrogen should contain 6.022 times 10 to the 23rd atoms of nitrogen. Okay, and that's because this is an element, and an element we talk about atoms. This final answer is 5.773 times 10 to the 21 atoms of nitrogen. All right. Oops. All right, so now we have oxygen, finally, to the end here. So we want to get to grams of oxygen. Well, we can't jump straight there. For me, I know that to get to grams of oxygen, I probably need to get to moles of oxygen first. Okay. How do I get to moles of oxygen? I need to get to moles of NH4 to SO4 first. Okay. And I already have that. So I have 4.793 times 10 to the negative 3 moles of NH4 to SO4. And I need to get to moles of oxygen first. So I see 4 moles of oxygen. So I have 4 moles of oxygen and 1 mole of ammonium sulfate. Okay? And then I know from the periodic table that oxygen weighs 16.0 grams in 1 mole of oxygen. And you'll see that this is just a single oxygen. It's not diatomic. When we're talking diatomic oxygen, that's oxygen all by its lonesome. Okay, that's not in a compound such as ammonium sulfate. All right, here we have moles of ammonium sulfate gone, moles of oxygen gone, leaving me only with grams of oxygen, which was my desired unit. That final answer is 0.3 0.068 grams of oxygen. Final answer. 4 sig figs here, 4 sig figs here, and all the way up we have 4 sig figs. Whew. Okay, so these unit conversions, pretty much what you need to really make sure you know is what can you convert directly to what. When you have moles, you can go mole ratio. When you need grams, you definitely need molar mass. That's going to be from the periodic table when you calculate the molar mass by adding up all the grams of each individual atom. And when you need some sort of particle, you have to use Avogadro's number. Particles are going to be atoms, formula units, or molecules, making sure you only use molecules with covalent compounds. All right, so hopefully you're just as worn out as I am. And let's go have some guacamole. I'm feeling some Mexican food now. All right, see you next time.